Welcome to the deep dive. Today, we're really getting into something fascinating. It seems complex, maybe, but it's about how electricity and magnetism work together. That old idea that they're kind of one thing.
Exactly.
Yeah.
It's fundamental to, well, so much of the technology around us,
Yeah.
how things move.
Right. And that's our mission today, isn't it? To sort of demystify how an electric motor actually spins. We want to make it super clear, especially, if you're just starting to wrap your head around this stuff.
hmm
We'll use something called Fleming's left-hand rule to break down the magic, if you will.
Yeah, it's a great tool for visualizing what's going on. It makes the invisible visible in a way.
Okay, so let's unpack this then before we jump right into motor spinning.
hmm
Let's really nail down this core idea. You've got electricity, right, flowing through a wire,
Yeah.
and that wire is sitting inside a magnetic field. What actually happens there?
Okay, so this is where it gets really interesting. It's not just, two separate things happening near each other. The magnetic field actually exerts a force on that wire carrying the current.
A force, like a physical push or pull.
Exactly that. A real measurable force. And this is the absolute key step, right? Turning electrical energy into actual physical movement.
Oh, okay.
And Fleming's left-hand rule is, well, it's like a little cheat sheet to figure out which direction that force is going to push or pull.
A cheat sheet. I like that. How does it work?
Okay, so imagine your left hand. You stick out your thumb, your first finger, and your middle finger. So they're all at right angles to each other, like three axes.
Right, got it. Thumb, forefinger, middle finger.
Yep. So your forefinger points in the direction of the magnetic field. Easy to remember, F for field, usually north to south.
Okay. Forefinger is field.
Your middle finger points in the direction of the current. Okay, maybe M for motion of charge, or just remember it's the second one for current.
Current. Okay.
And then your thumb, it points in the direction of the thrust, the force. That's the direction the wire gets pushed.
FBI, almost. Field, current, thrust. Thumb shows the force. Okay.
Exactly. It lets you predict the push.
That's really neat. So, okay, we have this principle. Current plus magnetic field equals predictable force. And you're saying this force, this push, that's the starting point for getting something to actually spin around.
Precisely. If you can control where that push happens, you can get rotation.
Okay, I think I'm getting the gist of idea. So how do we build on that? How do we get rotation from just a simple push? Let's build a really basic motor in our heads,
Yeah.
like the simplest possible version.
Perfect. Okay, picture this. You've got two magnets, a north pole facing a south pole.
All right.
So there's a magnetic field flowing across the gap between them, right? North to south.
Yep, got the field.
Now imagine we place a simple loop of wire, maybe square-shaped, right in the middle of that field.
Okay, a square wire loop sitting in the magnetic field.
Then we connect a battery so current starts flowing through this loop. And here's the key part. Let's say with the left side of the square, the current is flowing out towards you, coming out of the scene.
Out towards me on the left.
And on the right side, the current is flowing in, away from you, into the scene.
Okay, opposite directions on opposite sides.
Exactly. That opposition is crucial. Now, let's use Fleming's rule. Left hand out,
Okay.
left side first, field is left to right, forefinger.
Huh.
Current is out towards us, middle finger. Which way does your thumb point?
Field right, current out, thumb points up.
Up. Exactly. So there's an upward force on the left side of the wire.
Okay, upward push on the left.
Now the right side, field is still left to right,
Yeah.
forefinger. But the current is in, away from us,
Mm.
middle finger. Where does the thumb point now?
Field right, current in, thumb points down.
Down. Perfect. So a downward force on the right side.
Wow. Okay, so upward push on the left, downward pull on the right.
What's that going to do to the loop?
It's going to twist it. It'll make it rotate
Right.
clockwise.
Exactly. That's the torque. That twisting force that makes the loop start spinning clockwise.
That's it. That's the basic principle.
That's the absolute core of it. Turning electricity into rotation using these forces. Pretty elegant, right?
It really is. Okay, so we've got clockwise rotation down, but, what if you need it to spin the other way, like counterclockwise? Is it complicated to reverse it, or is there, like, a simple trick?
Oh, well, that's the beauty of it. It's actually incredibly simple. Based on Fleming's rule, what two things determine the force direction?
The field direction and the current direction.
Exactly. So to reverse the force, you just need to reverse one of those. You can flip the magnets, reverse the field.
Or just reverse the current.
Much easier, right? Just switch how you've connected the battery.
Ah, okay. So flip the battery connections.
Yep. So now think about the loop again.
Yeah.
If we reverse the current on the right side will now be coming out towards us.
Okay, right side is out.
And the current on the left side will be going in, away from us.
Left side is in, the opposite of before.
Exactly. So let's do Fleming's rule one more time. Left side, field right, current in,
Forces down,
down. Correct. And the right side,
field right, current out.
forces up. So now you have a downward force on the left and an upward force on the right.
Which means it rotates the other way, counterclockwise.
And there you have it. Just by reversing the current, you reverse the spin. Simple, predictable control.
That's brilliant. So it's all directly linked. Turn direction dictates rotation direction.
For these simple motors, absolutely.
Okay, this makes a lot of sense with the simple loop. But how does this connect to, like, real-world things? You know those little motors you find in, say, kids' toys? Or maybe, like, the small fan? Are they really working just like this?
They absolutely are. Fundamentally, yes.
Yeah.
Those are typically DC motors, direct current motors. They'll have permanent magnets north and south on the sides creating the field, just like we pictured.
Okay.
But instead of just one single wire loop, they use a coil.
A coil? What's that exactly?
It's basically the same wire, but it's wound around and around many, many times,
Yeah.
usually around an iron core.
Oh, like a whole bundle of loops together.
Precisely. And why do you think they do that? Why lots of turns instead of just one?
Well, if each loop gets that push, lots of loops would mean lots of push, a stronger rotation.
Exactly. Each turn of the wire adds its little bit of force, and when you bundle hundreds or thousands of turns together, you get a much, much stronger turning effect, more torque.
Makes sense. More wire interacting with the field means more overall force.
Right. Enough force to actually do work like spin a toy car's wheels or a fan blade.
Okay, so picture one of those toy motors. You hook up a battery, positive to one terminal, negative to the other, and it starts spinning, let's say, clockwise again.
Spinning away.
Now, what happens if you quickly swap the battery connections? Put the positive where the negative was and the negative where the positive was.
Well, based on what we just discussed, what did swapping the battery do in our simple loop example?
It reversed the current flow.
Right. What did reversing the current do?
It reversed the direction of the forces and reversed the rotation.
Exactly the same thing happens in the toy motor. Reversing the battery polarity reverses the current through the entire coil. And following Fleming's left-hand rule, this instantly flips the direction of the forces on all those wire turns.
So the motor just stops and spins the other way.
Pretty much instantly, yeah. It'll spin counterclockwise now.
Wow. So for these DC motors, it's a direct relationship. Battery polarity determines spin direction.
That's the key takeaway. Positive, negative one way gives you clockwise, flip it, and you get counterclockwise. Or vice versa, depending on how it's wound. But the principle holds.
So we've really gone from the basics of electricity meeting magnetism.
Yeah, that fundamental force.
Through visualizing the forces with Fleming's rule, seeing how it creates rotation, and even how to reverse it, and then connecting it straight to actual devices like toy motors. It feels like we've pulled back the curtain quite a bit.
I think so. It shows how these, seemingly abstract physics principles directly translate into practical working machines.
It really does. And when you think about it, how many things in our daily lives must use this exact principle? It's kind of mind-boggling.
It really is. Think about it for a second. Fans, of course. Blenders in the kitchen.
Oh, yeah, blenders. Electric toothbrushes.
Definitely. Power windows in a car. Drills. Computer hard drives, maybe the old spinning ones.
Wow, okay, it's everywhere. Refrigerators, washing machines.
Even things like pumps, conveyors, the list goes on and on.
Yeah.
This simple electromagnetic rotation is, well, it's a workhorse of modern technology.
So maybe the next time you hear that electric hum, whether it's your computer fan or, I don't know, a drone taking off, you can picture it, right? That dance inside, the current flowing, the magnetic field, and that resulting force just spinning away according to Fleming's rule.
Exactly. It's not magic. It's just this really elegant physics principle put to work.
Physics made it understandable, hopefully. Well, thank you so much for joining us on this deep dive today.
My pleasure.
Hopefully you look at all those spinning things around you with a little bit of new insight now. Thanks for listening.